I will now talk about a relative frequency and how it can be used to mimic the geometric distribution. A relative frequency can be approximated as probability by considering the long run behavior of repeated items or observation of events. So a relative frequency is defined as the ratio of number of events occur divided by the total number of trials. For a large number of trials, the relative frequency tends to stabilize around a certain value. That means it gets closer and closer to the probability of the event. Let us consider an example of a fair dice in which our aim is to get the number 3. So if we roll the die 3 times and we get 3 twice, the relative frequency is 2 by 10, that is 0.2. If we roll the dice 100 times and we get 3 18 times, then the relative frequency is 18 by 100, that's 0.18. If you roll the die 1000 times and you get 3 170 times, the relative frequency is 0.17. So similarly, if you continue to roll the dice more number of times, you will find that the relative frequency of getting 3 will get closer to the theoretical probability, which is close, which is 1 by 6. Now I will show the code which will explain how the relative frequency can be used to mimic the geometric distribution. The first two lines are for loading the Python modules. The next line specify an XPT 1000 specifies the number of experiment or trials. Then we specify the probability threshold. We want to find out how many attempts it to get the random number x that is less than or equal to 0.4. This line initializes an array of 0 with length 1000. This array will store the number of attempts it will take in each experiment to get a number less than 0.4. This is the outer loop which runs once for each experiment. So this will run 1000 times. This is the inner loop. It runs 500 times. And this line generates a uniform distribution random number between 0 and 1. This condition checks if the random number x which we are generating is less than or equal to 0.4. If the condition are met, it records the current random number g in the n attempt array for the current experiment. Also, all satisfying this condition will break this inner loop. These two lines are used for obtaining the minimum value and the maximum value from the n attempt array. So these two values will be used for creating the number of bins which will be used for plotting. So this line will be used for plotting. And we are also printing out the number of counts as well as the value for each outcome xy. So if you run this, you can see that we have a plot which is similar to that which we have obtained from the geometric distribution. So basically it has mimicked the value for that. Now in order to have a proper comparison, we print out the mean for the geometric distribution as well as what we did from the above. So if we run it, you can see that this loop, first we define the mean to be 0, and then we run for the number of bins, and using this we calculate the mean, and here we print out the mean for the relative frequency, and here is the mean obtained from the geometric distribution. If you compare it, you can see the value is quite close. So as we have talked about, like if we increase the number of trials, it should get close to the theoretical probability. So if we increase this value and run it again, you can see that the value is now much closer to the value of theoretical value, which is 2.5. And if we again run it by increasing this value, you can see that it is now much more closer to the theoretical value 2.5.